everyone, my name is Pol Francesch, and I'm here to present the work titled Fast Learning of Non-Cooperative Spacecraft 3D Models through Primitive Initialization that we did at the Space Rendezvous Lab at Stanford. Just a quick overview of what we'll be talking about today. I'll give a quick introduction, including the motivation, our problem statement, and kind of a review of the state of the art in this realm. I'll talk about our methodology, what results we achieved with our method, and I'll conclude with the way forward. To start with the motivation, the big topic really is on space sustainability and surveillance. As I'm sure we're all aware, the number of space objects is heavily increasing, especially as of late. And as that happens, space debris and bad actors need to be tracked, investigated, and even removed in order to maintain the safety of our current space assets and whatever future ones we might want to launch in the future. Due to the sheer number of these objects, to remain feasible in doing these actions, they must be done autonomously. And in some cases that involves sending a servicer that will need to estimate the shape and the pose of that target, be it space debris or a bad actor, on its own. With this, we come to our problem statement, which simply states that from a sequence of only RGB images, we want to be able to recover both a precise 3D model and the pose of an unknown non-cooperative target spacecraft. The motivation for these two different estimation goals, I guess, are the pose is really essential for getting safety. Without this, we don't know how far we are from the target, and so we can't know if we're being safe. And then the 3D model could be used to locate docking ports in the case that we want to rendezvous with the spacecraft, to determine faulty components, or to establish the target capabilities. There is related research in this work, and some of it has actually been to space. And it can be broadly categorized into three different sections here. The first one is on known target pose estimation. So the PRISMA mission was one of the first to perform uncooperative vision-based rendezvous, and recently certain methods have used learning-based methods in order to increase either the accuracy or to increase the robustness to illumination conditions. But all of these methods require known 3D models, which is not really the topic of this talk. To resolve the fact that sometimes the 3D model is unknown, some authors increase the sensor or mission complexity. So certain authors will use RGBD images, which include a depth map on top of the image, which you can get either from LiDAR or from stereo vision. And they use this to resolve the range and the scale of the target. Other authors have done synthetic stereo vision with multiple observer spacecraft, which obviously increases the mission complexity and makes it more difficult to launch them. The final category over here is kind of a mix and match of a couple different things. So some of them don't do precise shape estimates, which wouldn't allow us to know where the docking ports are, or what fault components are, what the capabilities are. And so, for example, a couple authors have worked on shape and pose estimates from a single CNN. I'll go more in depth on that in a second. But this only gives us coarse estimates, and we'd want precise 3D models. Other authors have tried training novel view synthesis methods, such as NERV for 3DGS. Novel view synthesis is a whole field that's come out of the terrestrial computer vision world. But it usually requires known poses of the target, which is maybe not available in space. And then other authors have tried to quickly initialize 3DGS models, since they take a long time to train using foundation models, but they're not trying to estimate the poses, which doesn't solve our safety issue. And so we see that the literature clearly lacks a way to efficiently learn precise 3D models with only RGB images without knowing the poses of the target. And the method that I'll present will leverage previous work in the CNN that I mentioned and 3D Gaussian splatting. Doesn't require any knowledge of the poses a priori. We train on a sequential incoming stream of RGB images, meaning that we don't have to wait for a whole batch of images to come in. We can do this from the get-go, and it does so quicker thanks to our proposed initialization method than anything else in the literature. So with this, we'll get over the overview of the method, which is best, I think, represented by this flowchart. So we start from a single incoming image, and we go into our initialization stage for our method. And this is really what the proposal is all about. Here we're feeding it to a CNN that we're dubbing the superquadratic CNN that I'll get into more detail in a second. And this gives us rotation, translation, and shape estimate that I dub as lambda here. From this, we sample a point cloud from the shape estimate, and we use this to initialize the 3D Gaussian splatting method. And then finally, this is a typical 3D Gaussian splatting training pipeline where we use the 3D Gaussians to render image, and we compare that to the ground truth image to get our loss, and then finally back propagate to get the optimization function. How do we get the poses? Because that was kind of part of my pitch, is we don't need poses a priori. Well, as I mentioned, the superquadratic CNN over here can also give us pose estimates. And so we use those online in order to train the 3D Gaussians. This is all a bit vague, so let me get into the detail, which requires some background. So let me start with the superquadratic CNN here. The superquadratic CNN is a CNN that was introduced, I think, in 2024, which, given a single RGB image, the CNN can estimate a coarse shape as a set of superquadratics and the pose with respect to the camera of a target. For those unfamiliar with superquadratics, they are shape primitives that can represent a variety of different shapes using a very small set of parameters. To give you an example, this is a set of superquadratics, so it's an assembly of them. Here I think there's 8, so each color represents a different superquadratic, and it gives you a sense that you can represent a lot of different shapes with them. This over here on your left is the notional CNN that we're using, which has an encoder and then 2 different heads for getting us the shape, and then finally the pose. Now, the original implementation of the CNN only released really 1 version, but 2 more have been released, and the differences between them are really in the way that they train on the rotation. So the first one directly trains the rotation estimate to estimate the reference truth without any kind of further stipulations. But what was noticed is that there's a bit of ambiguity in how you define the reference truth frame. And so you can unfortunately penalize your CNN from learning fully orientations if there's ambiguities in the way that your reference frame is defined. And so the follow-on work decided to create what they called an ambiguity-aware CNN, which didn't get penalized because it shows rotation estimates that are equivalent, but are off because of a mismatch in the reference frame definition. It also introduced the ambiguity-free version, which instead of estimating the rotation at all, it directly estimates the 3D model at the orientation of the current image. And so that means that the rotation estimate that it provides is identity, and instead the 3D model is actually oriented in that way. So you can imagine that this would be the 3D model estimated by the original and the ambiguity-aware CNNs, and then by the ambiguity-free CNN, on the other hand, it would be rotated by, for example, this spacecraft orientation. With that being said, let's talk about 3D Gaussian splatting, which is a novel resynthesis method that, given an incoming set of images, can render them with relatively high fidelity. So 3D Gaussian splatting parameterizes a scene or an object, whatever have you, with a collection of 3D Gaussians, which are parameterized as any other 3D Gaussian, with a mean, which gives you the location, and a covariance, which gives you the size and the shape. It also gives you an opacity, and the spherical harmonics are used for a view-dependent color. Now, to render an image using 3D Gaussian splatting, what we do is we place our camera in the real world in which the 3D Gaussians live. So you can imagine that this is a collection of thousands of Gaussians in the real world, and we're going to place our camera over here to the left. To render this image, what we'll do is we'll take an approximate projection transformation, and we'll project all of the Gaussians into the image plane, so to 2D, and then we'll call all of the Gaussians that are outside of the image plane because that would add additional compute and there's no need. Finally, they can get blended front to back in what's called alpha blending, where you take into account the opacity through a tile rasterizer, and we end up with a rendering that looks like this. To be clear, this process requires many more Gaussians than the one I'm showing in the slide, but at the end you do get renderings such as this one. With all that background kind of explained, let's talk about what we actually did in this work, which was initializing 3D Gaussian splatting through the superquadratic CNN primitives. To give some background, 3D Gaussian splatting is usually initialized through ColMap, which is a batch estimator, and usually requires a large amount of images in order to initialize. Instead, though, we can think about the fact that 3D Gaussians, if they have a covariance of 0, are just points, and so they would form a point cloud. And so what we could do is we had some initial mesh estimate of our model. We could sample a point cloud directly from that mesh, and use that point cloud in order to initialize 3D Gaussians instead of waiting for a batch of images to be available and then running ColMap. So that's exactly what we do. We take our first incoming image, we get the CNN to give us a mesh estimate, which is coarse. We sample a point cloud on that surface, and then we use that point cloud to directly initialize the 3D Gaussian splatting method. With the initialization kind of explained, let's talk about the poses that we're going to use in order to train 3D Gaussian splatting. So 2 out of the 3 CNN variants actually give us directly pose estimates. And so we're going to use those without any sort of filtering in order to train the 3D Gaussian model. The problem is that the third one, the ambiguity-free version, gives us absolutely no notion of the orientation except for implicitly. It's no longer an explicit representation, it's fully implicit. And so what we do is we do point cloud alignment between the first and the current mesh estimates from the ambiguity-free CNN in order to get the orientation estimate. To be precise, we do the point cloud alignment that minimizes the chamfer distance between that first time that we inference on the ambiguity-free CNN with that first image against our current image. You can imagine, if you are not aware of what point cloud alignment is, that you have 2 different 3D models sampled at different times. So, for example, our first 3D model that we got from the CNN is the blue one. And now, sometime later, we take another image and we get the red one. And we want to know the orientation between these two to then train 3D Gaussian sliding. So we can minimize the chamfer distance between them two. And then if you're successful, you will achieve these. And then this will require you to know the kind of relative orientation in order to minimize this. So then we can explicitly estimate the orientation from the point cloud alignment. So now we see we have 3 different CNN variants that at some point can give us explicit pose estimates. With this kind of method fully run through, we'll first show results where we use the reference truth poses. Unfortunately, 3D Gaussians are actually a little bit, they require pretty precise pose estimates, and so you'll see that later down the line, you lose some fidelity when we train with the estimated pose estimates. So it's nice to see the full capability, and then we'll get into what happens when we use the full pipeline. In this table, I'm showing you 3 different kinds of metrics. So the first set that you see in the first 3 rows are the training metrics. So they're the ones that are trained, used to train the 3D Gaussians. The second set are purely evaluation metrics. They're just helpful for us to get an idea of how the training is going. And the final set are timing metrics. So how quickly are things moving? What we demonstrate is that compared to this first column, which is just a random initialization of the 3D Gaussians, the 3 different CNN flavors provide higher reconstruction quality, and this is seen both through lower loss values and better evaluation metric values, and also faster to get there, even though they have longer initialization times. So obviously initializing randomly is completely free, but we overcome this cost of initialization with 3D models that are trained faster and end up being better. To show this visually, we have these videos here. What you'll see here is a constant render target. So this is what the 3D Gaussians will try to render. And what you see on the bottom are the 2 different initialization methods that we propose, so the random and the one initialized by the superquadrics, as they are trained over time. And then finally on these graphs, you'll see the loss and the LPEPS metric, again, as it's being trained over time. What you'll see is that the initial 3D model from the superquadrics is already quite good. So all it needs to do is do some refinement and to do color matching. And we see actually that for the amount of time that we train, it is actually imperative to have the superquadric initialization because it's the only time that we actually learn about the solar panels. We otherwise completely miss them. This satellite, though, we're cheating a little bit. It's actually in the training set of the CNN. So let's talk about a satellite that's not in the training set, it's in the test set. So the CNN has never seen the satellite. That's why this initial shape estimate is a bit poor. But our training method is actually able to overcome this, remove these fake kind of appendages in the satellite, and completely learn the true 3D model, whereas the randomization is incapable. It learns about the bus, but not the solar panels. With that being said, and those results shown, let's talk about online pose estimation before we try training with these poses. So these are the results from the errors that we get from the different CNN flavors on the different dataset splits. And what you're seeing here is that the orientation error is always quite poor. And what I'll tell you is that 60 degrees is worse than 45 degrees. I think we can all kind of agree on that. But is it really that much better? The answer is no, but what's actually better is the nature of the error. And I think this is best represented by this image. So in this image, what we're showing is, again, the image that we're feeding to the CNN, and then the rows represent what the CNN is outputting, oriented by the orientation estimate. So here, for example, we fed this image to the original CNN, it outputs a mesh and an orientation estimate, and then we rotated the mesh and projected it to DD to then show it to you in this image. It's really clear what the nature of these orientations are, especially in the deep space satellite. So you can see that in the original and the ambiguity-aware network, the orientation errors are sort of random. They're all over the place. You could believe that these are 60 degrees off, but clearly the solar panels are in the wrong location. In the case of the ambiguity-free network, though, it's providing us coarse rotation estimates, but at the very least, the solar panels are in the right location. And this is actually key for being able to learn all of the features of the spacecraft. Once again, I'm showing the same table. This time we did more testing, and that's because we have different sources of pose. So we still have the random initialization, which is used at our baseline, and then it's fed with poses from the different CNN flavors. And then we also have the superquadratic initialization that is once again fed from the different flavors. Once again, we show that the metrics are much better in the sense that we get better loss using the ambiguity-free network and better PSNR and outlips values using as well the ambiguity-free. What is much worse this time is the timing. So here we see the cost of the point cloud alignment coming up very clearly. Whereas before we were training in about 10 seconds at most, we're now taking about 500 seconds to learn precise 3D models, simply because of the cost of point cloud alignment. Here I'm once again showing the same sort of video, but this time we're training on those pose estimates. And you're seeing that the resulting 3D model is poorer than before, simply because of those coarse pose estimates. But it is for the most part capable of learning that there are solar panels, that there is a bus, and that they are different, whereas the randomization is once again incapable of learning those. One more time, we do this with the test set satellite, and we show kind of similar behavior where we are doing worse than with the reference truth poses, which is expected, given the kinds of errors that we see, but still better than randomization. With all this said, I think from this results, we can clearly see that initializing the 3D Gaussian splatting with superquadratic primitives is successful in reducing the computational load that's required in order to implement this method in space. And it also increases the accuracy, especially when the poses are available. When the poses are not available, the initialization is really key to overcoming those coarse pose estimates. In terms of ways forward, what we see here is that something that we've done is we've used these superquadratics as primitives, we sample some sort of point cloud, and then we move on to using the 3D Gaussians. But we could have used the superquadratics all the way through and tried to render them directly. Something we'd also really like to do is to improve the point cloud alignment. There's no particular reason that it should be so costly. There are certainly better ways to do this. And then finally, we'd also like to improve the single shot pose estimates to kind of use different pose sources. And the last thing is obviously then to test on space and space-like imagery and processors to really validate and ensure that this method is capable of dealing with the harsh lighting and low compute regimes. Thank you. That's